So we resume with the last one for today, that is Hitoshi, and he's going to continue on the same topic as yesterday on the microscopic theories for the TeV with the slides you see. So Hitoshi, the floor is yours.
Okay, thank you. So let me get started, continuing on the subject we talked about yesterday. So the last thing we talked about is the fact that when you look at this potential over here, it really looks like a toy model, and it very much resembles what is called the Ginzburg-Landau theory in superconductivity. But in the case of superconductivity, we have a more fundamental theory called the BCS theory, where you have two electrons near Fermi surface that get attracted by the phonon exchange over here. And that is a predictive theory because then you can compute what is the penetration depth is, which corresponds to the mass of the W boson in particle physics context, or what is called the coherence length is, which corresponds to the mass of the Higgs boson in particle physics is, and in terms of the fundamental parameters of the material. So in the same way, we were hoping to reach a deeper level of understanding what's behind this potential in the standard model. And the one thing people notice, this idea that what the standard model does is to be a part of this SU2 cross SU2 breaking down to SU2, which is very much what the QC-like theory does. That's why people try to model the electric symmetry breaking based on the QC-like dynamics. And that was the idea called Technicolor. I told you how the theory looks like. But in the end, I told you also that this idea died at least 3 times. So this idea didn't pan out, unfortunately. So what I like to then point out is that, so this technical theory was based on this idea that what breaks the electric symmetry is actually a fermion bilinear composite object. Let me go back to the case when the scalar is actually elementary. And what would actually look like when you think about this mass parameter m Higgs squared in the potential, which has to be negative, so that you have a minimum L squared away from the origin. And if you take this parameter and put that into the renormalization group equation, and as a function of energy scale, it turns out that the mh squared runs together with the energy scale squared. So the running actually looks like this. And I don't know what this original energy scale is really, but let's say it's something like m Planck squared. And then you start with the positive mh mass squared of the order of the positive Planck scale squared, and keeps running as a straight line all the way down to the energy scale of the Z mass, where you need to find a slightly negative, like 100 GeV squared scale in this running. And this was actually the reason why people didn't feel comfortable with the standard model, namely that if you actually choose some initial energy scale, whatever that is, that may be high energy scale, you need to choose the initial condition somewhere so that this would actually shoot down all the way to nearly zero in a way precisely that actually crosses zero, basically. And that is of the order of, in the case of the Planck scale, that is 10 to the minus 34 level of fine-tuning in the initial condition. And that's what many people didn't like. And of course, you can say that, well, maybe the dimensional regularization removes the quadratic divergence. But if you actually do dimensional regularization, you have to integrate out whatever heavy particles you might have at the Planck scale or gut scale. And that actually does produce a correction to Higgs mass scale of the order of that energy scale. So even if you use dim reg, you don't really get rid of the quadratic divergence in the presence of extra physics at very high energy scales. So that's what people wanted to somehow resolve and come up with a better theory, which doesn't have this issue. And that was the idea behind supersymmetry. And many of you know the supersymmetry is the idea that you have a symmetry that can relate boson to fermion. So if we have a quark in the standard model, then you have a boson partner that spins zero, and it's called the scalar quark or squark. And if we have a fermion lepton, Then you have its scalar partner, lepton. On the other hand, in the case of the boson, we have in a standard model named Higgs. You have its fermionic partner, which we called Higgs-Xenos. And similarly, when you have a boson, which is spin 1, like W and Z, we have Wino, Xeno, photon to photino, gluon to gluino. So this is the way the particle content works out when you have supersymmetry. And the point here is that you actually have tons of the spin 0 particles once you make the theory supersymmetric, because every quark has a supersymmetric partner that's spin 0. Every lepton, including the neutrino, has a superpartner has spin 0. So for each generation, you have new 15 complex scalar particles. For 3 generations, that's 45 altogether. Then you have Higgs. So it turns out that Higgs is actually a one of many, many spin 0 particles in the theory. And also that when you look at the renormalization group equation, not that it runs like linear in energy squared in RGE, it turns out that this behaves only logarithmically as a function of energy scale, very similar to the running of the gauge coupling constant. And we have no idea what these matches are at some high energy scale. Well, let's say they are approximately the same. Then if you solve the renormalization group equations for mass squared over each of these spin 0 particles, you can see that quarks actually get enhanced at low energies because of the QCD coupling effects. Leptons are also enhanced, but not as much because it doesn't have the strong coupling. It's only electroweak coupling. And what's special about the Higgs is that it has the large top Yukawa coupling, and top quark loop actually giving you a negative sign, so that Higgs actually receives a contribution which can potentially go to negative value at the low energies. And in many parts of Parmenides space, even if you vary this initial condition, you find that this kind of pattern, that the quarks and leptons all become heavier, while Higgs is the only spin 0 particle that ends up receiving negative correction, and therefore total mass square ends up being negative. And that would, of course, gives the shape of the potential that looks like this, not like that. So that will lead to the electroweak symmetry. Oops. Here we go. Electroweak symmetry. So this way, you can actually explain why SU2 plus U1 is broken, but not SU3 color or U1 doing D. Because particles which have these charges have the positive mass squared, and therefore they no longer acquire excitation values. But Higgs is the only one that ends up acquiring excitation value and breaking SU2 plus U1. So that at least would give us a better understanding on what's behind the symmetry breaking in the standard model. So this idea is very different from what we saw in Technicolor in QC-like theory. And this has a name, which is called radiative breaking. Because symmetry breaking happens because of the radiative corrections or RGE effects, renormalization group equation effects, happening on the mass squared of the Higgs boson. And of course, you all know the supersymmetry had not been discovered either, so they have to be somewhat heavy. So now it's getting a little bit fine-tuned. I will come back and talk about this maybe tomorrow. But anyway, this actually gives you an idea what we are talking about, a potentially more fundamental theory of electric symmetry breaking. So namely that the idea here is that we would like to understand electroweak symmetry breaking. That would require a deeper theory, which may be happening at the energy scale somewhat heavier than the Z mass scale, so TeV or possibly 10 TeV and so on. But we are looking for such a theory. So that has not changed even since the discovery of the Higgs boson. And there are some other issues I would like to talk about and come back tomorrow later, which has to do with the naturalness and the context for having a spin zero particle. And you might be used to the idea of seeing the Higgs boson in Lagrangian already because that's in the textbook. But in retrospect, that is actually a very difficult thing to swallow because we have never seen such a particle yet. So that's why we are still talking about getting a better understanding of electrical symmetry breaking, how everything works, how do we understand the particle content in the standard model. And then you also can further ask the question about the flavor, TeV violation, baryon asymmetry, and possibly adding issue of dark matter, dark energy, and inflation. So there are many things we haven't understood yet, which are proven and shown already by a lot of data, but we have no clues about. So putting them everything together, it's clear that standard model is not the end of the story. So that's where we are. Now, let me also come back and talk a little bit about the history on when we feel we attain a better understanding of what's going on at the energy scale. That's past history. One. And when we are talking about this mass spectrum of the particles, mesons and baryons, here's zero. You have very light pions, kaons, eta prime, and you may add rho and omega over here. And it turns out that there are also a whole lot of zero plus particles at low energies, which are believed to be actually tetraquarks, which have this upside down spectrum, the sigma, A star, and A1. And so they're believed to be oops, P2 bar states for tetraquarks. So these states exist. So these are not mesons. And then you have baryons. You have proton, neutron, and you have delta. You have 4 of them. And then you have also the lambda, sigma, and sigma stars and omega, and so on and so forth. So you have these baryons. So we really struggle to understand this energy spectrum, the spectrum of the hadrons in the history. But at the end of the day, we came to this picture that there's this confinement scale, which is about TeV, where quarks and leptons, the quarks and gluons at high energies, are now confined into hadrons. And that's where you have pions in other energy scales that are here. But if you go up, we have tau, j psi, upsilon, eventually mz, where we actually see and measure this running of alpha sub s very precisely by experiments. So we know that there is a world of the perturbably interacting quarks and gluons at high energies, and their interactions become stronger and stronger as you go down to lower energies around the GeV energy scale. And tau mass scale is the biggest coupling you can really measure reliably. That's why it's about 0.2, whereas MC is about 1.12, that's 0.12. And once coupling becomes strong, at least it is conceivable that this very strong coupling would bind quarks together and confine them inside hadrons so that we would not observe isolated quarks anymore. So the reason why we at least feel confident and comfortable with this picture is that we are observing this very complicated world of hadrons from high energy scales down. So if you could see physics from top to bottom, then you feel like you understand what's going on. And that's the kind of understanding we would like to get in the case of the weak theory as well. And in the case of the weak interactions, we did start with this 4 fermion interactions the Fermi told us, and we mentioned this actually yesterday. And let's think about, for example, some hypothetical experiment where you collide electrons and electron antineutrinos. Certainly, I don't think we can build such a collider in practice, but just for the purpose of a Gedanken experiment, we can talk about that. And so in this case, because the coupling constant is the Fermi constant, whose dimension is -2, the amplitude of the scattering process should be proportional to this coupling, but make sure that the amplitude is dimensionless. You have to actually supply something with the energy scale squared. The only thing in this case is the Mandelstam variable S. And I hope everybody knows the notation that S is basically twice center of mass energy of this collision square. And the Mandelstam is actually one of my late colleagues, so I need to actually write his name down. And whenever you have a collision process, particles P1 and P2 coming in, and particles of momentum P3 and P4 going out, you define 3 Mandelstam variables. S is the total momentum squared in the initial state, which is obviously the same as that in the final state. P is momentum transfer between P3 and P1. U is the cross channel of that. So these are the Mandelstam variables. So what I'm talking about here is S, which is this definition that happens to be simply just the center of mass energy squared. So the amplitude, if we just go ahead and compute it, really does look something like this. There's actually T dependence too, but for the sake of argument, I am ignoring it. So if you actually plot this amplitude as a function of energy scale, is S, and amplitude grows linearly with S. But there is something called a unitarity limit, which basically restricts the M to be about less than 1. Unitarity limit. Which is basically an expression of the statement that the probability can never be bigger than 100%. So the size of the amplitude, which is related to the probability of the scattering, has to be linear assumption. And so in this unit, it turns out to be about 1. So it looks like if you take this amplitude at the face value, you end up violating unitarity. So quantum mechanics is wrong in that case. And certainly we don't think that is the right conclusion out of this. So what this is telling us is that something must happen before the amplitude hits the unitarity limit to save the day, to make sure that amplitude actually ends up never exceeding the unitarity limit. And it turns out what happened in the history is that you find a resonance over here, which is nothing but a W boson that would replace this diagram by the exchange of W. So it appears as an S channel, the resonance over here. And above this resonance, it actually stays low and more or less constant and ends up never exceeding the unitarity limit. So this is the way we could actually make this original theory by Fermi, which was clearly an effective low energy theory and needs to be completed into renormalizable theory, could be actually replaced by the theory that has a W boson in it. And that's the theory we all learn in textbook. But the story doesn't end there, because when you actually look at another kind of process, like W plus, W minus coming in, scatter into the same particles, Again, we don't have the W plus W minus collider, but as we will talk about, we can get something which closely resembles the W plus W minus collider if you manage to go to 10 TeV muon collider. That's the subject of this tool. That's why this is actually not an academic exercise anymore. And what's happening here is that when you actually take the longitudinal polarization of this W boson, you all know the polarization vector of, for example, a particle that is going in the z direction may look something like this, or the transverse polarization of elastic +1 and -1. But for the longitudinal polarization, actually looks rather odd because it's actually greatly enhanced when actually the energy of the W boson is very large, and it's actually proportional to gamma and gamma beta. And I could have actually written this momentum also using the gamma and gamma beta, just a standard practice in relativistic kinematics. So this is MW, gamma, 0, 0, gamma beta, where gamma is 1 over square root 1 minus beta. Beta is the velocity over c. I hope that's you're familiar with this notation. So whenever you have a actually large the momentum, then I should erase this. So this polarization vector is very large, proportional to gamma. So when you're talking about, like, for example, like the 10 TeV W boson, if again actually produce such a state, then compared to the mass of W boson of 80 GeV, roughly 100, gamma is order 100. So each of these wave functions here carries a power of 100. So naively, the amplitude is enhanced by 100 to the 4th power. That's 10 to the 8th. And that certainly is way beyond any unitarity limit. What's going on here is that when you actually compute this diagram in the standard model, you have P-channel diagram, you exchange gamma and Z. You also have S-channel diagram, again, gamma and Z. There is also what we call the contact interaction. And there's a big cancellation happening among them of the order of 10 to minus 4. So your amplitude ends up being, again, Fermi constant times S. That's something you can easily see. So because you have 2 powers of gauge couplings there, and you have the enhancement of energy of the W over mass of the W squared. And we have learned that W mass is 1/4 V squared V squared. So for getting this factor 1/4, if we put that in, this is indeed energy over V squared. And 1 over V squared is indeed the Fermi constant we talked about yesterday too. So summing these diagrams up, you still have this growing amplitude. And what should happen in this case is that there are 2 more diagrams now that we have discovered Higgs boson, which needs to be excluded. And also T-channel. So you see the same phenomenon that you have this growing amplitude, which would eventually hit the unitarity limit. But there's a resonance here that would actually cut off the rise. And in practice, this can never be the real W scattering into the H resonance just because the Higgs mass will not be lighter than twice the W mass. But again, it's a Gedanken experiment. So you see the idea. That's a very similar thing that happened here. So this is the way we now think that the standard model could, in principle, be UV complete. But to really make sure that is the case, you have to look at every channel, which also includes process like this one. So WW to Higgs 6, again, in principle, has a growing amplitude. But if you add up all the diagrams that exist in the process, and then you find everything cancel out so that everything actually turns out to be order the constant, a zero power in energy scale. And this is what is called unitarity cancellation. As a matter of fact, when you're talking about the energy of W and Z boson, including Higgs, much bigger than their masses, you can imagine a world where electroweak is restored. Then this potential is nothing but phi1 squared, phi2 squared, phi3 squared, plus phi2 squared. That's an SO4 sigma model. And in this Lagrangian, these states, phi1 to phi2, phi3, phi4, really does correspond to the Z, W plus, W minus, and Higgs. So if you go to high enough energies, you should be able to confirm that all of these particles become basically identical with each other. They should behave exactly the same way. And at the same time, all the amplitudes are unitary and with no growing component. And that's the determination of actually looking at the physics of the electric scale from top down, just like what we did with the QCD, so that now we will finally feel like we understand what's going on. The point I'm making here is that we certainly have not gotten there. So that is another thing we should aim at high energies. And what we actually do in high energies, even though I said this W plus W minus collision is an Gedanken experiment, you can think about doing the muon collider experiment where muon go to mu bar, mu minus goes to mu. Here I should have probably drawn the arrows backwards. W mu plus emits the W plus, mu minus emits the W minus, and they really scatter in the middle and go to WW, ZZ, or XX. And then we should be able to really observe the electrically scale physics from above the energy scale down so that we can check if we understand everything correctly. And in fact, in this diagram I drew on the previous slide, there's one coupling we have never measured in any experiment so far, which is the coupling of the Higgs boson with itself. And also we would like to measure this coupling much better. And that's why the people are talking about the E plus or minus 6 factory and why E plus or minus is a good thing. I will come back and talk about it in a moment. But in the end, what the only message I'd like to convey here is that all of the things that are really fundamental to understanding of electroweak symmetry and how that's broken, giving rise to the low energy physics of the standard electroweak physics, are not being tested yet, because we have not measured some of the important couplings in town. We have never tested equivalence of W and Z boson with the Higgs boson yet. So there are still many things to be tested experimentally so that we feel now that we finally understand what's going on there. But in order to do this experiment, it's clear that we need to go to very high energies. And in fact, if people have talked about the center mass energy of E plus E minus experiment, around 1.5 TeV is the absolute minimum to start testing these WW scattering process. So that's why we are talking about even higher energies in collider experiments. Now, some of you asked this question in a question answer session. So why are we talking about 10 TeV mu plus and mu minus when we also at the same time talking about 100 TeV proton machine, which may be 85 now, depending on the magnet technology, but here we're talking about the ballpark numbers. And I responded to the question, but let me actually be a little bit more precise here. So when you're talking about the proton-proton collision, proton comes in very high energies, So it's actually more like a pancake. It actually looks something like that, because the Lorentz contraction of the proton of mass of 1 GeV accelerate to 50 GeV is really squashed in the longitudinal direction by factor of 50,000. So this is actually even thinner than pancake. But anyway, so that's why we are colliding against each other. And out of this collision of protons, which looks like a pancake, you extract one element inside the proton, which we call protons, which may be quark or gluon. And they actually collide and do something in the middle and produce some interesting physics in there. But this proton I, which may be quark or gluon, carries only a fraction of the original momentum of the proton momentum. So this is the momentum of this proton, which is only xi times the original momentum of the proton. And the same is also true on this side. So this is the other proton. So the center of mass collision here, which we always put this hat on it when we talk about this subsystem, is given by xi xj times the center of mass energy squared of the original TeV collision. And this is actually always less than 1, and you multiply them twice. So in the end, it turns out that 100 TeV TP roughly probes in TeV the proton center of mass energy and so you're not be able to actually use the full center of mass energy of the proton-proton collision. On the other hand, in the case of the mu-mu collider, muon is an elementary particle, so you can use the full center of mass energy of the mu plus mu minus system to produce anything that is interesting out there. So you can really use the full center of mass energy of the mu plus mu minus collision. So in this case, 10 TeV mu mu is really 10 TeV proton center of mass, which turns out to be comparable to 100 TeV PP machine. And that's why we are talking about them in parallel. So in order to reach 10 TeV energy scale in, for example, WW scattering process we are interested in, the total center of mass energy of 10 TeV is definitely way above 1.5 TeV, so we can actually do this. And to do the same thing in a proton-proton collision, you instead need something like 100 TeV collider. So that's why we talk about both of them in parallel. And I hope this point is clear, and because this, I'm sure it will come up later on. So we write down the cross-section of the proton-proton collision that produces something interesting final state is always given in terms of integral. With what is called the proton distribution function. PDF for short, which is unfortunately very confusing with the portable document format from Adobe, which we use all the time, but then it's called PDF nonetheless. And so this actually tells you the probability of finding a proton I, let's say a quark, inside a proton with a momentum fraction xi. So the fraction can be always less than 1, so it's integrated over 0 to 1. And same on the other side. And then you fold this on top of the subsystem cross-section, where subsystem has only a fraction of the total center energy of the PP collision. So this is the way we compute the probability for the proton-proton collision. And the sort of the cartoon way of understanding what this proton distribution function looks like is that you start with a picture. The proton is really made of 3 quarks. So each quark carrying 1/3 of the energy of the proton. And you have 1 down quark, you have 2 up quarks, So the probability is twice as large for up quark compared to down quark, but it's meant to be on top of each other at x equal to 1/3. But this is, of course, too naive because the quarks are contained inside the proton. They can move on their own motion. So this actually gets spread out a little bit. But in addition, when you observe quark at a very high resolution with a microscope at a very high momentum transfer, then you can see the quark can split into quark and gluon. Gluon can further split into quark and antiquarks and so on and so forth. So that would actually produce additional component at a lower fraction, momentum fraction. So at the end of the day, the only way to do justice is to draw this on log scale. And here's like 1.2, 0.8, 0.4. And this peak around 1/3 is still there for up quark and down quark. But when you produce these virtual quark pairs, they would contribute at lower momentum fraction like this. So this is called C quark for both quark and antiquark. But the gluon really shoots up like this one, where it's usually normalized by a 10th factor to make the gluon fit on the same scale. So that's why if you go to high energies, the proton-proton collision is basically a glue-glue collision. It's a glue-ball collider. I did mention that in responding to some of the questions yesterday. So this is how it looks like in proton-proton collision. And looking at this proton distribution function, it's clear that you can never really use one for the proton energy to make use of the full center mass energy of the proton-proton center mass energy. So that is meant to be basically a quick explanation of what I mentioned by Wars yesterday, why 100 TeV take the proton-proton collider and 10 TeV muon plus muon collider can be discussed in parallel in terms of doing similar physics at the end of the day. And here I'm still just talking about the overall energy scale. When you look at some particular processes, there could be more differences between PP and mu collisions, but we'll get back to that only later. But at this stage, I really would like to focus on this big picture, namely that we thought we wanted to go to the Fermi scale. And instead of building a globotron, thanks to our accelerator friends, we managed to come up with a collider technology that at least it becomes thinkable to reach the energy scale of the TeV, which we did with LHC and discovered Higgs boson. But we haven't finished the job because we haven't understood the underlying mechanism why this Higgs-Gluon symmetry is broken at all. And to understand this, just like what we did with the strong interaction, we would like to jump ahead to energy higher than TeV and look down at it so that we get a full understanding of what's going on, so that we do want to reach this 10 TeV kind of proton center mass energy scale. And for this purpose, we are now talking about this one path of building 10 TeV-ish mu plus mu minus collider or 100 TeV-ish proton-proton collider. And in principle, one can imagine also that they're developing technology, possibly using plasma wave field, that you can use the 10 TeV E plus E minus collider as well. And all of them are still subject to R&D, hence no clear decision has been made on which way to go, as far as I'm concerned. Of course, the European strategy process may come up with a different answer on this question, but this is the way I view where we are today. So we do have to go to 10 TeV energy scale, that we can look down on the electroweak scale to get a full understanding of what's going on. We already know this energy scale is important, so you like to go ahead and jump ahead to go to high energies because of that. And for that purpose, we have several candidates, fortunately, to choose from. Once the technology matures, then we hope that we can build at least one of them. But even if we actually do have one of them, in an ideal world, having multiple of them actually give us a complementary tools, looking at the same physics from different angles. So that will be the best of the whole world. So that's why we're talking about 10 TeV, the muon collider. But there are more advantages talking about the lepton colliders beyond this issue of being able to use the full center mass energy. So when you do the proton-to-proton collision, you're making use of only one proton out of each of the proton. But you have many other protons which are left there, which are called spectators, which may just get into the beam pipe, but then they also cause scattering on their own. So you end up actually producing a whole lot of junks near the beam direction, which is called a minimum biasing. So the environment where you use the proton-proton collision is very messy to begin with. In addition, because there are so many photons that have color and they have a strong interaction in it, you can also produce some particles actually going fairly off, away from the beam axis. So many of them are really concentrated in this beam direction. But if you something coming out at a large angle, then you actually end up detecting in a barrel portion of the detector. So you have to actually deal with them. And this is called the initial stage radiation. And simply because the strong coupling constant is strong of the order of 0.1 instead of 0.01, this also happens all the time as well. And that would also give you additional complication to the environment you have to work with. And furthermore, you see this kind of collision happening, actually something like a hundreds I'm not very good at this. But pileups, the possibly 100,000 of them per each time beams cross inside the detector. So that would also place a very significant demand on how you can design a detector. And again, I'm not an expert on this. I'm sure Kevin will spend a lot of time talking about this issue. And so that's another technical problem we have to deal with. But in terms of physics, what's the biggest loss in this process is because you are losing so many particles down in the beam direction, what is called the longitudinal direction. So you actually lose information longitudinal momentum, DL. So whatever is actually going on in this direction, you have very little information on. So you actually lose a lot of information on the kinematic constraint. And the kinematic constraints actually turned out to be extremely useful when you talk about the lepton collider. And so that's actually one thing I would like to emphasize in the next few minutes. And there's another advantage for the lepton collider. So when you actually have the muon beam, let's say mu plus, it can also split in the same way that the gluons and quarks split into additional protons. And W plus may further split into W plus and Z and so on and so forth. So this kind of splitting process really does happen. But unlike in the case of the proton, this initial condition is something you can only determine by experiment because there's no first principle way, at least known to us, to compute this proton distribution function. And once you have measured it at certain energy scales, you can evolve it to another energy scale using this DG-LAP equation, Dokshitz, Gribov, Lipatov, Autorelli-Parisi equation, I think. Yeah. So that's something you learn in textbook about QCD. But you need to give the initial condition from somewhere else. So this is actually not a first principle calculation. So whatever you can predict on the proton-proton fission, it's always limited by the uncertainties in the experimental knowledge of the determining proton distribution functions. And that's something we still have to deal with very seriously in any of the light analysis in TeV collision. So for the case of the lepton, even though the leptons do split in a similar way, I described for the quarks and gluons, you can do this in a first principle. It's calculable from first principles. So this way, you have, in principle, a complete control on what these processes should look like in vector colliders, because you can calculate everything and compare them against data. And one big advantage, though, is that the process in a lepton-lepton collider is much, much smaller than the cross-section you can observe in proton-proton collider, because the proton has many protons inside, and many of the interactions happen due to strong interaction. So it turns out that cross-section is much, much smaller. So the gaining enough statistics is much more of a challenge at the lepton collider. But within the limited statistics, you can extract a whole lot more information from lepton collider than you can from the proton collider. And that's something I'd like to actually show you by looking at the real pictures. So at this point, I'd like to stop sharing my tablet and instead go to a slide where I'd like to show some of the real pictures on how E plus E minus events actually look like. And are you seeing the slides okay? Does it look good, Roberto?
We see Atlas.
Yeah, then it's fine. And so you all know the experiments happening at the Large Hadron Collider today. You rely on these humongous detectors like Atlas, a CMS where C stands for compact, but still humongous. But anyway, so these are the experiments we're doing today. And I'm sure Kevin explained some rough idea on how detectors work. Each component is responsible for detecting different kinds of particles. The muon spectrometer for the muons, which penetrate everything. Hadrons will produce a shower in the hadron calorimeter, and the electron and photon produce the electromagnetic shower, so they actually stop before getting into the hadron calorimeter. So the shower here is either electron or photon, and you can tell them apart depending on whether you have a track for the electron or no track for the photon. And pi plus, pi minus protons would eventually show these tracks in addition to the shower and the hadron calorimeter. And so that's the way you basically tell what particles are produced in the experiment. And what I would like to show is actually going 20 years earlier when people are doing the experiment called LEP, Large Electron Positron Collider, LEP. That's very inventive name. But I'm showing some pictures, which I still happen to have from an experiment named Aleph. And the basic concept is the same, even though the technology was the old-time technology. There was no silicon blue detector, for instance, with a drift chamber, for instance, quickly. So the technology is old, but nonetheless the same idea. But what I'd like to show you is how clear understanding you can gain just by even looking at the pictures. So this is the event display where electron is coming from your side into the screen, positron is coming from the other side of the screen into the screen. They collide in the middle, and this is sort of projection on along the beam direction of what the event looks like. You clearly see two particles produced from this collision. In this case, E plus E minus produces Z boson. Z boson decayed into two particles. You see a track, so it's the charged particle, and produces a shower in electromagnetic calorimeter on both sides. So it has to be an electron instead of other particles. So this is a Z decay into E plus E minus. So you can see what's going on very, very clearly just by looking at them. This is clearly a Z decay into QQ bar. And I don't know which quark that is. It's very difficult to determine. And if it's a B quark, then you can zoom up here in the vertex vector and see a displaced vertex, so you can tell with a fairly good efficiency. But nonetheless, it's clear it's the QQ bar events. It produces many pions, and those actually produce hits in hadron calorimeter together with tracks. pi naught decays immediately into gamma gamma, and gamma is for shallow electromagnetic calorimeter. You see them as well. And so this is mostly these light halos that are producing hits both in electromagnetic calorimeter and hadronic calorimeter. Here, you see hits in a muon chamber. So this is a Z decaying to mu plus mu minus. This is interesting. You see one mu here, another mu here, another hit in the electromagnetic calorimeter with no track. So this is photon. So Z decays to mu plus mu minus. Now either mu plus or mu minus radiated a hard photon. And again, you can even see a Feynman diagram just by looking at this event display. So this is actually something you might need to a little bit think about. So here you see one particle with a track with the deposit in the electromagnetic calorimeter. So this is clearly electron. Here you see three tracks, some deposits in the electromagnetic calorimeter, some in the hadronic calorimeter. So they are hadrons of some sort, but they are very correlated, not very large number of them. So this is actually clearly a Z to tau tau. So one of the taus decayed into electron, muon, neutrino, antineutrino. The other tau decayed into neutrino and hadrons, like in this case, maybe 5 pions, pi plus, pi minus, pi 0, let's say. So it's something like that. So again, you can tell immediately these are tau. And these are two jet events. V going to QQ bar, one of the quarks radiate a hard gluon. This is a fourth jet event where one gluon may split further into two gluons, or the quarks may emit another gluon out of it. So this is the way you can understand the fourth jet event. If you go to higher energies like LEP2, you can produce W pairs. So in this case, you can clearly see 4 jets coming from 2 Ws. And if you open up the 4 pi, you see 4 clear clusters of the hadronic particles. Here you see one direction momentum is missing. And this is clearly neutrino. On the other hand, the recording particle here, it stops in the electromagnetic calorimeter. This is actually electron. So you can tell that this is actually WW event, where one W decays to QQ bar, another W decays to electron and neutrino. And this is also clearly something missing over here. So in this case, you see hits in a muon chamber and in the barrel, but also down here, you see actually hits in the, I forgot where that was. Oh, here, on the edge. So then this is actually one W decaying to mu nu, another W also decaying to, I'm sorry. So this is muon, this is the electron. So one W decaying to mu nu, another W decaying to E nu. So you see that. So in this case, you see hits a muon chamber again, but something missing in this area. So that's clearly shown in this 4 pi picture. So one W decaying to QQ bar, another W decaying to muon and neutrino. And so on and so forth. I probably don't need to go to here. You can clearly see a tau again. So this is W to mu nu, W to tau nu. And the reason why I'm showing this picture is that because of the clarity of event, looking down at the QCD scale, we have really helped us understand QCD itself. So looking at these 4-jet event, oh, I'm sorry, this is actually yet another ZZ event before getting the QCD. So here, if we blow this up, you see it displays blue text. So this has to be 4 jets of two Zs, one Z decaying to BD bar. And just to remind you that W basically doesn't decay into B quark at all, because the bottom quark is partnered with top quark. W cannot decay into TeV bar just because top is heavier than W boson. So when you see a bottom quark in jets at this energy, it really has to be Z boson. So once you see 4 jets with the bottom quark in it, you already know this will be Z instead of W plus W minus. But anyway, coming back to jets and understand QCD. So here's the 2 jet events I talked about. So even though each quark hadronizes and become a bunch of hadrons, just by looking at it, you can tell basically the one of the quarks must have been going in this direction, the other quark going in the other direction. And looking at the angle, the total angle of the quarks coming out of the Z decay, you can actually determine the spin of the quark. And looking at the quark has a spin 1/2, due to angular momentum conservation, you can tell that angular distribution has to be 1 plus cosine theta squared. That's this distribution. And because unfortunately you can't tell quark and anti-quark apart in the hadronic events, you need to follow the forward and backward direction. The cosine theta goes only from 0 to 1 instead of -1 to 1, because you can't tell which way is forward, which way is backward. But this is, again, the 1 plus cosine squared theta curve. When you add this 1 plus cosine theta and 1 minus cosine theta squared, and then you find this 1 plus cosine squared theta as a prediction if the quark has spin 1/2. But if the quark were spin 0 particle, then again, and from angular momentum conservation, you can't produce particle in a forward direction. So the angular distribution is supposed to look like sine squared theta. That's this histogram in Monte Carlo down here. And data points in black clearly show it's actually spin 1/2. And you might think this is a trivial exercise because we learned that quarks are spin 1/2 in the standard model textbook. But how do we know that experimentally? Well, all we see are these jets. We don't see the quarks, isolated quarks, never, because they're confined. But this way, you can really measure the spin of the quarks and confirm the QCD is the right description for it. And when you have a spinor events, because you're producing additional gluon, you get information on the gluon too. So gluon, again, we know it has to be spin 1, but just hypothetically think about the gluon being spin 0. And once again, they produce different angular distributions, as shown in these histograms. And the data points clearly favor this red dashed curve, which corresponds to vector gluon, namely the spin 1. So this is the way we can measure the gluon to have spin 1. And further going to certain forward events, where the additional gluon can further split into glue-glue. That comes from this non-abelian interaction of gluon to gluon. Or gluon can split into QQ bar, or two QQ bar each can emit a gluon on their own. So there are several processes involved, and one of them is this push or non-abelian vertex among the gluons, which should be part of this final state of the forward events. So by fitting the angular distribution of these forward events, you can really extract these group theory factors in these the non-abelian gauge theory, and really confirm that SU3 in this asterisk is the only group that fits within this ellipse allowed by the data. So that's what we mean that we clearly understand it. If you go up to the high energy scale, look down at what we used to study with the big mysteries, this is the way you can be sure that you have actually gained full understanding of it. And that's also true with electroweak coupling. But this is one of the most beautiful measurements I have seen in plus minus of left. For example, looking at the tau to pi nu, you can fit energy spectrum of this pion by two components. One of them rises with energy. One of them goes down with energy. They correspond to two different tau polarizations. Because if you produce a tau minus, that decays to new tau, because of both tau minus with the left-handed helicity with a new tau would favor the same direction. So pion tends to have a lower energy. So that's how you can get this distribution in energy spectrum in magenta. But if tau is right-handed, they tend to emit a neutrino that's left-handed in the backward direction. The pion tends to be harder. That's this blue component. And by just by filling this one-dimensional histogram, you can extract how polarized tau is, which came after Z decay. And this is a fundamental measurement you can do on a Z coupling to different particle species. In particular, left-handed and right-handed particles couple the Z bosons differently because in standard model is a chiral gauge theory, and you can really extract that piece of information. And to be able to do so, you need to know how much neutrino is gone from the system. And for this, you really need to understand how much energy momentum is conserved without losing in the longitudinal direction. So we can do this kind of measurements only because we have the full kinematic constraint in an E plus E minus or lepton collider environment in general. So what we hope to discuss tomorrow is by looking at this virtue of the lepton colliders, which we have already seen in the past, what we can do better in future now combining our renewed the motivation to study weak physics top down from high energy scale, using this kind of environment where you can do the first principle calculations, normalization for every processes, you can extract all kinematic information out of the final state. Even the statistics is much lower than the corresponding TeV counterpart, you can get a whole lot more information out of the actual events in a very clear way, as you already see in event displays. Okay, so let me stop here for today and then take some questions from the audience.
Questions? I see already one.
Hi, I have a question about what you were mentioning at the beginning with the running of the Higgs mass and supersymmetry. I think, like, very naively, I would assume that if we're correcting for, like, numerically what the Higgs mass should be, then we would have a very solid idea of what all the supersymmetric masses should be. But it seems like there's a lot of different models that would predict different masses for the supersymmetric particles.
Yeah, unfortunately, that's the case. So let me see if I can go back to the slide. Yeah, this one here, right?
Yes.
So when you try to do this renormalization group running, you need to specify the initial conditions. And here, for simplicity, I assume that every spin zero particle have the same mass to begin with. But of course, that's an oversimplification. And inside this running, you also need to provide a mass of the gauge genos, Luino, Zeno, Gluino into the calculations. That's yet another free parameters. So there are quite a few free parameters in this calculation. This generic trend that Higgs boson is the only one that's likely to acquire negative mass squared at the end of the day is true. That's a generic trend. But actual quantitative details depend on all these additional parameters. So unfortunately, this renormalization with calculations is not really powerful enough to pin down on every parameter we need to know. That's why we are still left with this uncertainty where the superparticles are supposed to be, and indeed we didn't find them so far, but they could be still, down around the corner, and we just don't know. Does that answer your question?
She's nodding.
Oh, okay.
Yes, thank you.
Okay. By the way, I always joke that talking the superparticle gluons gluino is a misnomer. We have to change at some point because ino means a little cute guy like bambino, but the gluino is a humongously heavy object. So instead of calling it gluino, I always argue that it should be called gluissimo. I hope Italians will like that idea, but it never stuck in the community.
All right. More questions? Moment. Hi, thank you for the talk. In one of the first slides, you talked about how you can test the electroweak symmetry when it's restored using WW scattering in plus-minus collisions. But considering the splitting of the muon, you have that the energy scale for the WW collision is actually peaked at the electroweak scale, if I'm not wrong, with some tail to the TeV scale. So is the tail, let's say, enough? Does it give you enough statistics to test the unbroken electroweak symmetry, or is it a limiting factor?
Yes, the answer is yes. And I don't know where I actually wrote on the slide, but I was actually one of the first people who managed to compute these WW scattering process in E plus C minus collision by writing the core of what eventually became math graph. And we could determine that at the center of mass energy 1.5 TeV, you could already start testing whether the scattering would reach the unitarity limit or not. So but that was barely enough. If you go to multi-TeV, like 3 or possibly 10, then you're comfortably above that energy scale, that you can start extracting a lot more information about this WW scattering. And one thing I will point out tomorrow too is that this kind of W fusion process actually grows with the center of mass energy. On the other hand, the typical annihilation cross-section goes like 1 of energy squared. So as we go to higher and higher energies, W fusion process becomes more and more dominant, or vector fusion in general, including photon, because they are logarithmically enhanced to high energies. So you get more data that way. And yeah, that's the way it really helps to go to high energies.
Okay, thank you. Sorry, so just to continue on this topic. So let's suppose you find some deviation in the WW scattering behavior at high energies. Just as an experimentalist, I would ask myself, what kind of models can predict this kind of behavior? What kind of hints you can get from this kind of deviation?
Yeah, so just by having multiple Higgses rather than just a single Higgs boson in the standard model, that already poses a big deviation in it, because you change this coupling. So if the electrovicinity breaking is shared among different components, several components, each Higgs has less of that, and so it can actually be responsible of doing this unitarity cancellation only partially. So here you're comparing two big numbers, and because of this precise cancellation that happens for the standard model, you end up with a small amplitude, and that's what theory predicts. But if there are multiple Higgses in there, then each two big ones may not have the right normalization. So even if you add them, you still have a big leftover, and that big leftover can be canceled only when you go above additional Higgs state energy scale. So just by changing the Higgs sector a little bit, you can actually observe big impact on this WW scattering process.
Okay. Any more questions for Hitoshi for today? I remind you, we have Hitoshi twice tomorrow, before lunch and after lunch.
You have too many of them.
Well, actually, you already answered one of the questions that was in the question sheet.
Oh,
So,
okay.
Thank you for that. And thank you again for joining us today.